physics. My talk will be about the direct neutrino mass search with KATRIN. After introduction, I would like to tell you how the KATRIN experiment works. I will show you first commissioning data. I will show you what is our sensitivity on the neutrino mass before I will conclude. Just since I'm the first in a series of direct neutrino mass experiment, I would like to remind you that we have 3 ways to the absolute neutrino mass scale. We have yesterday had a very nice talk by Over about the cosmology analysis on neutrino masses. We had already many talks about the search for neutrinos double beta decay. I should remind you that both are in different ways model dependent. They require Majorana neutrinos, and we are heavily discussing about the quenching of GA. The direct neutrino mass determination doesn't require any further assumptions. It just uses the relativistic energy momentum relationship. Therefore, m square is the observable. You can, of course, dream of time of flight measurements, but the uncertainties of supernova explosions, the current uncertainties, do not allow you, even if you would observe one tomorrow in our galaxy, to get sub-electron volt limits, and the current limit from supernova 1987 is 5.7 electron volts. What we do is we investigate kinematics of weak decays. By that we measure charge decay products and use just the energy momentum relation to deduce the mass of the neutrino. We look at tritium beta decay and nowadays also very strongly in helium electron capture. Before we go to that, I would like to stress a fact which was already mentioned in the discussion, that there are uncertainties and different relations. I think I have to disagree a very little bit to Francesco. The rest was very fine. The electron neutrino mass is really defined as the invariant sum of all mass eigenstates contributing to the electron neutrino, and that is the effective electron neutrino mass, which has all these phases in which you observe in double beta decay. If you plot both against the sum of all neutrino mass eigenstate observed in cosmology, you see that only the direct neutrino mass measurement has a 1-to-1 relation for normal in inverted hierarchy, and you have a band because of the unknown CP phases in case of neutrinoless double beta decay. In addition, there are the uncertainties of the nuclear matrix element and the quenching factor, and the uncertainties that this double beta decay without neutrinos can be propagated maybe by NASA particles and a heavy neutrino. So my summary of that is that the absolute scale or the cosmological relevant neutrino mass in the lab has to be measured by single beta decay. I completely underline what Aman said. Double beta decay has much other important things like lepton number violation. In the direct determination, for example, in tritium beta decay, we look for the endpoint spectrum of an allowed beta decay, which is governed by a phase space factor. And with tritium beta decay, if you look at the very endpoint, the phase space factor gets sensitive to the neutrino mass. Just by kinematical reasons, the beta spectrum rises quadratically if the neutrino mass is non-zero and deviates a little bit if the mass is non-zero. That little deviation allows you to measure the neutrino mass, but please keep in mind, if an endpoint is as low as tritium with 18.6 keV, this gray shaded area, which corresponds to a neutrino mass of 1 electron volt, amounts only to 2 times 10 to the minus 3, which means it's an extremely tiny effect. So previous experiments have excluded neutrinos to play a dominant role in the dark matter problem. To go a next step, you need a very low endpoint, like tritium can do, and you will hear more about electron capture experiments with holmium directly after the coffee break. And you need very high energy resolution, high luminosity, and low background really to discover the neutrino mass. And that means you need the technology of a McE filter or cryobolometers. Let me just briefly remind you what a McE filter is. It's you have a tritium source and a detector which is schematically connected by magnetic field lines of superconducting magnets that allows you to get this high solid acceptance. But on the way to the middle of the spectrometer, there is a very strong magnetic gradient, and the magnetic gradient force aligns the momenta parallel to the magnetic field lines. You can then run against an electrostatic potential, and only those electrons which have enough energy are accelerated and detected. Therefore, this spectrometer is an integrating spectrometer with a step-like function, and the step width is only defined by the ratio of the magnetic field and is less than an electron volt in case of KATRIN. It's a very sharp function which outtails, so systematics are extremely low of these kind of instruments. Now let me show you the KATRIN experiment. It's a 7-meter long setup consisting of a huge McE filter of that type. The beta electrons are produced by decay in a windowless gaseous tritium source. There's a decay rate of 10 to the 11 electrons per second. 10 to the 10 are going in forward direction in the imaged flux tube. There's a tritium retention and pumping and an electron transport section, a first spectrometer, this huge high energy resolution spectrometer, and a counting detector. With that setup, KATRIN will reach a sensitivity of 200 millielectron volts. It's being built and commissioned at the moment at Karlsruhe Institute of Technology in Germany, and being built by an international collaboration of 20 institutions from 6 countries. Let me start with the molecular windowless gaseous tritium source. It's essentially a 10-meter long tube of 9 centimeter diameter embedded in a system of superconducting solenoids at 30 Kelvin. Tritium is injected in the middle, and it's freely streaming out to both sides, where it's pumped back and recirculated. At our inlet pressure of 3 microbar, we accumulate a column density of 5 times 10 to the 17 molecules per square centimeter. Since our count rate near the endpoint scales with the column density, but then saturates because of inelastic scattering, which takes away energy from the electron, and then the electron is gone for the endpoint region, we run at about 90% optimal column density. By that, we inject nearly 5 curie per tritium per second. The windowless gaseous tritium source has been installed at Karlsruhe. Here you see an older picture at the manufacturing place. Here you see the whole system installed. It's of course a fisheye picture. The whole thing is straight. It needs a lot of cryogenics control, but it's operated very nicely. Behind the windowless gaseous tritium source, at the very end of our setup, there's a calibration monitoring weir system. It consists of 3 essential things. It first has a photoelectron gun to shoot electrons from the very back, for example through the windowless gaseous tritium source, to be analyzed by the spectrometer to measure column density and the energy loss spectrum. It also is good to control the spectrometer transmission. Secondly, there is a rear wall with a little hole for the electron beam, which can be opened and closed, which defines the source potential and neutralizes the tritium plasma to a level of 10 to 20 millivolt. And finally, we have X-ray detectors to do online monitoring of the tritium amount of our dynamic tritium source. Here you see it's all housed in a second containment because of its tritium content. Behind the windowless gaseous tritium source, downstream towards the spectrometer, there is a 2-fold system to retain tritium. First, by differential pumping, where you have superconducting solenoids intersected by large turbomolecular pumps. What you also see is an arrangement like a chicane that molecules can't fly straight through the setup. They are neutral, they will be redirected to the pumps and pumped away. If you have ions, they can be magnetically guided, of course, and for that we have 2 systems to get rid of them by electric dipoles and by monopoles, and we can measure by a fast Fourier transform ion cyclotron resonance trap the ion rate. Behind that, we have a cryogenic chicane at 3 to 4 Kelvin operating in, again, superconducting magnets. To increase the pumping efficiency, we have on the stainless steel at 3 to 4 Kelvin an argon snow, which enhances the surface and therefore the tritium gather capability. Again, the system is in full operation. Inside the cryogenic pumping section, there are 2 monitoring and calibration systems. It's a so-called forward beam monitor, which can go to every point of our flux tube with a pin diode and measure the count rate. And we have a calibration source, a condensed krypton 83M conversion electron source, which is a frozen source on a very pure graphite substrate, which is cleaned by an ablation laser and monitored by an ellipsometry laser. Again, it can cover every point of the flux tube. Behind that, we have the tandem of the spectrometers, and I told you already about this energy resolution of 0.93 electron volt, and that is achieved by lowering the magnetic field by a factor of 20,000. On the same way, it explains the big size of the spectrometer because of magnetic flux conservation. It has a huge volume. It's the largest ultra-high vacuum tank ever been built, and a large surface. It runs at ultra-high vacuum of 10 to the minus 11 millibar region, and the whole spectrometer acts as a retarding spectrometer, so don't put your hands on the spectrometer when it's in operation. It's on high voltage. Of course, there's a fence around it. This high voltage has a ppm precision. I will come to that. You have seen yesterday in Over's talk that it's a big beast. The inner wall is covered by a double-layer wire electrode system to shield from cosmic muon-induced backgrounds. They are huge pumps with a total pumping speed nearly of 1 million liters per second behind liquid nitrogen baffles, and the whole system is surrounded by a large air coil system to shape the magnetic field, to suppress the Earth's magnetic field or compensate, and to do the background suppression. Behind that, there is a state-of-the-art electron counting detector, which is a pixelized silicon detector of 9 centimeter diameter with 148 pixels, with about an keV energy resolution embedded in a superconducting magnets inside a passive and an active shield. We have commissioned the main spectrometer more than 2 years ago by shooting electrons from a pulse angular selective photoelectron source through the spectrometer on different field lines and checking by our pixelated detector where they end up. You see here the transmission function is even sharper than this 0.3 electron volt because it's mono-angular source. So 0.93 electron volt are only reached if you have an isotropic source. We see the transmission is shifted because we have a potential variation over the not infinitely long spectrometer, which we understand it's a parabola shape, and the different transmission points depend on the angle you assign the electrons to start with. We have checked our backgrounds. We have identified 8 sources of backgrounds. Most of them we knew. We could avoid and fight up to now 7 of them by many tricks. I don't go into these technical details. I tell you maybe about fine-shaped special electrodes, the wire electrodes on the outside liquid nitrogen baffles, special symmetries of magnetic fields. But we have one background which is a background nobody else has observed yet, which is special for these spectrometers. And it's something interesting from the physics point of view, but annoying from the background point of view. If you have alpha emitters implanted in the surface of this big spectrometer as a remedy from radon decays in air, if you install your spectrometer, you have air. So every wall here in the room will have the same properties. They sputter off atoms. These atoms might be in excited Rydberg state, and these are neutral, therefore they can penetrate our magnetic field and electrostatic barrier, but they are highly excited, so short-lived, and they get de-excited by the black body radiation of a room at 300 Kelvin. So they eject very low energy electrons in the middle of the spectrometer, where these electrons follow the magnetic field lines, get accelerated, and hit the detector with exactly the energy our beta electrons will have. We have checked whether this strange hypothesis is true by many means. I will show you the most impressive one. We have injected a short-lived isotope radon-220 from a thorium-228 source. And when we open it, we see an increase of background of this typical background. When we close the valve again, we see the half-life of the daughter lead-212 very nicely in our background. So we understand that. We are at the moment trying different countermeasures like extended bakeout phase. It's done, it helped a bit. Strong ultraviolet illumination that is under investigation. It's not so clear whether that helps, but we have several other methods at the end which we will try out sooner or later. In October a year ago, we started our first light campaign. We shot electrons from the rear wall, from the very back, through the whole setup, through the spectrometer to the detector. And we also shot ions from a special ion source to the spectrometer. And all worked. We tested alignment, magnetic steering of a pencil beam, and also ion detection and ion removal. So we were all excited, but no tritium yet. In July this year, we had a very special campaign to check really the tritium source. Still without tritium, we injected krypton-83m, that isotope which is a noble gas, which you have known before. It emits several sharp electron line, conversion electron line, and a few Auger lines around the tritium endpoint up to 32 keV. We injected that from a gigabecquerel rubidium-83 source into the tritium source, and we monitored with a spectrometer the electrons and did spectroscopy on them. We also run the condensed krypton conversion electron source, which I showed quickly, but we also run a third conversion electron source of krypton-83m with our monitor spectrometer, which is a high voltage measurement device. Here I show you just some preliminary data. We have not published data. It's low statistics. It's only a very small fraction of our statistics. But you see nicely, for example, the L332 line, which has a gamma width of 1.4 electron volt and at 30.5 keV, that we see that transmission function when we lower the retarding potential. If you deconvolute, you see the nice Lorentzian. We checked, for example, is our high voltage system stable over time, over 5 days? You see our error budget for the systematics is 60 millielectron volt, and you see that we stabilize the source below 10 millivolt range at 30 kilovolts. That is sub-ppm level, which is also extremely nice. We have more scans on all the other lines. We have a very sharp doublet with 670 fine splitting. We have n sub electron volt natural width that is background free, and that is all currently being analyzed. I would like to show you one special detail just to tell you about the precision and the technology KATRIN has developed. We measure, in addition to the monitor spectrometer, our high voltage with a dedicated set of high voltage dividers, which we developed together with the German Natural Meteorological Institute. It's a ppm device. Of this, there exists 3 in the world, 1 at PTB, 2 at KATRIN. So it's really frontier technology. And that is a calibration constant, the scale factor. It's given here to 8 digits from a measurement campaign in 2013. It's just electro-engineering measurement. Now, we can use our krypton line. Unfortunately, we don't know the line position so well because the gamma transition is only known to 500 millielectron volts. But we can take the L3 line and the K line and just take the difference. The difference is then governed not by the gamma transition, which is not well known, but just by the known uncertainties of the atomic binding energies, which is less than 1 order of magnitude smaller. And you can go through the numbers. You can then do the difference, and most of the systematics drop out. And it's very interesting to obtain 4 years later, by a very different method, the same scale factor with 5 ppm precision, which is only governed by the knowledge of electron binding energies in krypton and nothing else. And so our high voltage scale factor is staying stable at the ppm level over 4 years, which is essential for KATRIN. Thanks. Now coming to the neutrino mass sensitivity, here you see the expected tritium spectrum which we would see on a log scale. We will have different fit parameters which are unknown, the endpoint energy, the neutrino mass square, of course our observable, the absolute amplitude, and the background. A 5 sigma signal would, without being noticed, would show up in a very strange residual, so we would directly see a neutrino mass. To optimally get sensitive to the neutrino mass, we put a lot of count measurement time to the endpoint region and also distribute a little bit for the background and to disentangle endpoint energy and amplitude. By that, we would reach our envisaged sensitivity after 3 years of full data taking, but very quickly we approach interesting regions. Just to give you a flavor of how we disentangle systematics, I told you about the energy loss measurement where we shoot in electrons from different, from the back through the windowless gaseous tritium source. Running with different column densities, we would obtain signals of transmission like that. Here you see the electrons which get delayed through the spectrometer because they lost inelastically energy. We can simulate such measurement and deconvolute at the computer, and we can prove that our methods are nice enough for our purpose. We have a very intense modeling of our tritium source. We have using state-of-the-art nuclear and molecular theory. Here you see the electronic and vibration rotation final state. That is a rotation vibrational prodding of the ground state, and here you see overlaid with electronic final state of T2 molecular beta decay. And here you see some figures of our gas dynamic modeling where we include longitudinal and radial pressure, density, temperature profiles, the plasma potential, and the magnetic field model. This brings us to systematic uncertainties, which are plotted here in blue. If you add them up, they are comparable to the statistical error bar for 3 years data taken. These values of the statistical error bar refers to 10 millicounts per second background. I told you that we have a problem of higher background by these Rydberg atoms, and if we do that, we can modify a little bit the strategy to how to measure. We enlarge the region below the endpoint, which we can easily do because we got much better than we anticipated 13 years ago when we wrote the design report in many of our systematics. And that would lead to a sensitivity not of 200, but presently of 240 millielectron volt, without that we find some further mitigation strategy for the Rydberg background. If we of course find something, and then we will go lower than 240, maybe towards the envisaged 200 millielectron volt again. I should also stress at the end that we are not only looking to the neutrino mass, KATRIN is also sensitive to sterile neutrinos. The beta spectrum, which I showed at the beginning of my talk, will appear twofold if we have not only the light neutrino masses, which we cannot disentangle, and a heavy neutrino mass with a mixing sinus squared theta and cosinus squared theta. Let's talk about electron neutrinos, which are motivated by the so-called reactor neutrino anomaly. You have this red band of possible evidence for mixing angle and delta m square, and we can cover this area very sufficiently with 3 years of KATRIN data taking. Discussing KV sterile neutrinos, we have also handled to look on a larger scale on the beta spectrum, and you find publications here. We can also look for other signals of physics beyond the standard model, for example, for non-standard model currents, where you have right-handed currents in connection with sterile neutrinos, which gives you nice features near the endpoint. Please have in mind, KATRIN will be the most precise endpoint measurement of a super allowed beta spectrum ever been done. That brings me in time to my conclusion, Manfred. The direct neutrino mass experiments, of which you will hear about Project A, TOLMS, ECHO, more talks in this conference, is complementary to cosmology analysis and double beta decay. All of them can look in different ways to sterile neutrinos in the electron volt and keV range and other beyond the standard model physics. KATRIN is the direct neutrino mass experiment with 200 millielectron volt sensitivity. Our system is completed, except the tritium loops, where still some little work is to be done. The rear wall and some calibration system is not completely finished. We celebrated first light in October last year. We had a very successful krypton calibration campaign in July 2017, so this year, and tritium data taking will start next year. And that will be accompanied by the KATRIN inauguration ceremony on June 11 next year, directly after Neutrino 2018 at Heidelberg, where I think most of you will come. So on behalf of KATRIN, I would like to thank you for your attention.
Yeah.